So in fact, I will talk about coherence in low-energy charge exchange collision, but not only with oriented targets. In fact, this is the outline of my talk. I will first introduce the charge exchange process, as well as the context and aims of our study, and then we will consider the case of charge exchange with non-oriented targets, and in particular, the case of atomic matter wave diffraction patterns, which appears in the distribution of scattered projectiles subsequent to charge exchange. I will present the theoretical description and then the experimental setup, which is based on recoil ion momentum spectroscopy, that is RIMS, coupled to a magneto-optical trapping technique to access very low temperature of the targets and then very high resolution. Then we will see how this MOTRIM setup enables to reveal the diffraction pattern expected from theory. Then, in a second part, I will consider the charge exchange from oriented targets. We will see how the MOTRIM setup has been modified in order to obtain oriented targets. Then I will present the theoretical description, focusing on coherence and interferential features of the dynamics. And interestingly, we will see that in that case, this is the experiment which allows to probe the accuracy of the theoretical description. Then I will terminate with conclusions and perspective. So first, the context. Charge exchange is a process which occurs as an ion with impact velocity v and impact parameter b collides on an atomic or molecular target. As the projectile crosses the target, it captures one or many electrons of the target, and this is what is called charge exchange, CE, or electron capture. CE is particularly efficient in the so-called low impact velocity regime. That is when the impact velocity v is smaller or of the same order of magnitude of the initial velocity of the electron on its orbit. CE is of practical interest in many applications, ranging from fusion plasma physics to astrophysics. I give here some illustrations which are issued from a science paper of Cravens. This first picture is the X-ray spectrum of this comet taken by the Chandra telescope. Interestingly, we can see that only the front edge of the comet, which faces the sun, appear in the X-ray spectrum. And it has been found that this X-ray emission is due to the radiative decay of the excited ions formed through charge exchange between the highly charged ions of the solar wind and the neutral species of the cometopause. And by analyzing such a spectrum and some additional ones, Cravens and co-workers were able to deduce the ionic composition of the solar wind. Besides some interesting application as this, C is of fundamental interest as the probe of non-adiabatic electron processes in few-body moving systems. But here, total cross-sections are not sufficient. In fact, the mechanisms which underlie the reaction processes are encoded in the differential cross-section, the DCS, which are nothing else than the distribution of scattered projectiles after charge exchange. I will illustrate here how a projectile is scattered after charge exchange from an isotropic initial target. And we see that there is an obvious cylindrical symmetry with respect to the direction of the incident beam, so that the differential cross-section does not depend on the angle phi, but only on the deflection angle theta. And interestingly, we can see that the deflection angle theta is related to the impact parameter b, where the transition occurs, through this simple relationship. In fact, this relation is issued from the classical description of scattering. In this respect, it is only indicative, in so much as dynamics in the low velocity regime are never totally classical. As a matter of fact, we will see that in the semi-classical or quantum description of scattering, various nuclear trajectories with distinct b can contribute to the same deflection angle theta. But we understand that if we measure the DCS as a function of theta, we can infer some information about the transition occurring at the given impact parameter b. Furthermore, measurements are usually accompanied by simulation, and there is a strong interplay between simulation and measurement. For instance, from simulation, one can infer some expected feature of the dynamics, but they have to be verified by the measurement. This is typically the case of diffraction. And reversely, the measurements are necessary to test the accuracy of the theoretical description. And we will see that this is typically the case in the case of oriented targets. So now our aims. And first, the passage from theory to measurement with the case of atomic matter wave diffraction patterns in charge exchange from non-oriented targets. Although I will present later on a detailed description of the charge exchange dynamics, we intuitively understand that charge exchange occurs provided the projectile passes quite close to the target. Otherwise, the projectile cannot catch the electrons. So I say here that CE occurs within a finite range of impact parameters, let's say B less or equal to B max. In this respect, the CE wave, that is all the nuclear trajectories which are of interest for a given charge exchange process, consist of a hole of radius B max. And then the analogy with usual optics is clear. That is all the nuclear trajectories with distinct B, which gives the same deflection angle theta, are coherent, then diffraction pattern should appear in the associated DCS. The expected angular spacing between the fringes is this one. It is inversely proportional to B max, and it depends on lambda, where lambda is the Debray wavelength associated to the incoming beam. In 2001, Van der Poel and co-workers demonstrated this effect in lithium plus sodium collision. And very nice diffraction patterns were resolved using a Mottrim's technique, which is quite similar to that I will present later on. But for collision involving heavier species, the diffraction pattern could not be resolved for two reasons. Because of the prohibitively large reduced mass of the collision system, and so a very small angular spacing, and because of the limited resolution of the setup. This is why we decided to reinvestigate the case of CE diffraction in sodium plus rubidium collision using the Mottrim setup, which is available in Caen, in France. But before entering into this part, it should be mentioned that within the interplay between theory and measurement, there is now the experimental resolution which can be achieved nowadays is so good that experiments are stringent to theory. And in particular, we will see from the theoretical side that the DCS are nothing else than the square modulus of the scattering amplitude. And provided that the initial and final state are suitably characterized, some experiments, which we call quantum mechanical experiments, are able to access the scattering amplitudes. I present here such a case with a rubidium atom placed in a well-defined and oriented 5p plus 1 state. Here we see that the orientation of the initial state destroys the cylindrical symmetry with respect to the direction of the incoming beam. In fact, because of the rotation of the electron cloud inherent in the orientation, we see that left and right scattering cannot be identical. Why? While the down and up symmetry is conserved. Accordingly, the DCS will present a left-right asymmetry, and we will see that this asymmetry encodes coherence and interferences feature of the underlying dynamics. This is very fine and very important information which will be used to probe the limitation and to improve our theoretical description of charge exchange. So now, let's enter into the first part of my talk, which is about the diffraction in the CE DCS. I will first present the theoretical description in order to understand why and how some diffraction patterns are expected in the DCS. So we work with the semi-classical molecular orbital cross-coupling calculation, MOCC. And in this approach, the nuclear motion is described classically. That is, a projectile follows rectilinear trajectory with impact velocity v and impact parameter b. The electron motion is described quantum mechanically within the single active electron approximation. That is, we assume that only the valence electron of the rubidium atom will be involved in the dynamics, whereas the inner electrons of both the target and the projectile will remain frozen throughout the collision. The resulting one electron Hamiltonian is written here, with the kinetic energy part, with the electron target and electron projectile interactions, which includes the interaction of the active electron with the nuclei, but also with the frozen inner electrons within a mean field approach. And finally, the core-core interaction, which is usually restricted to the first order terms, that is the Coulombic repulsion between the sodium plus and rubidium plus terms. Then the electron motion is described by solving the aconal equation, which is equivalent to the time-dependent Schrödinger equation, and that for each nuclear trajectory characterized by V and B. To do this, we expand the total electronic wave function on a set of molecular states of the sodium rubidium plus molecules formed during the collision. These molecular states are obviously correlated to either sodium and rubidium atomic state in the limit of infinite nuclear separation. So we can describe excitation and capture processes. Once the coefficient of the expansion are known, we compute the differential cross-section, the DCS, as the square modulus of the scattering amplitude. And the relation between the expansion coefficient and the scattering amplitude is given here. Here, G is a Bessel function of the first kind. Interestingly, we see that the scattering amplitude involves an integration on B. That is, it involves the coherent superposition of all the nuclear trajectory with distinct B, which will lead to the same theta phi scattering angles. Accordingly, interferences and diffraction patterns should appear in the differential cross-section. Once we have the definition of the DCS and scattering amplitude, the analogy with usual diffraction in optics is obvious. It is written here. And in this case, the function A of B will correspond to the radial distribution of the light through the hole. Then now I turn to the Motrim setup. So the measurement of the DCS is based on recoil-ion momentum spectroscopy, RIMS, which is quite known. Here, there is a scheme for the in-plane kinematics. The projectiles arrives with a momentum pi, is scattered with a momentum pf, while the target recoils with a momentum pr. So we know the entry channel, and we can identify the final channel by looking at the potential energy defect, or Q value, between the entry and final state. And we see here that the Q value is directly related to the parallel component of the recoil-ion momentum, whereas the scattering angle, theta, is directly proportional to the perpendicular or transverse component of the recoil-ion momentum. Then, within RIMS, 2 of the 3 Cartesian coordinates of PR are deduced from the position of position-sensitive detectors here, whereas the 3rd Cartesian coordinate is deduced from the time of flight of the recoil-ion. And the resolution achieved by RIMS is very good, so that the main limitation of RIMS in terms of resolution on Q and theta value is the target temperature. This is why, this is why we have called the RIMS technique to the MOT. The technique of a MOT is quite known. It uses a static magnetic field, which is provided by anti-Helmholtz coils, coupled to 6 counterpropagating laser beams, which are cyclically polarized, and which ensure the confinement of the atom through the mechanisms of photon absorption and associated radiation pressure. Here is a picture of the trapped cloud. Its dimension is typically 1 millimeter with a density greater than 10 to 11 atoms per cubic centimeters, and the temperature is lower than 200 microkelvin. The temperature is so low that with Motrims, the resolution, the final resolution obtained on Q and theta is the one given by the RIMS spectrometer. In other words, the target temperature does not degrade at all the resolutions that we have. And here I give some number in cases of 2 keV, sodium plus, and rubidium collisions. So now, let's turn to the results. Even though we have measured and computed a lot of cross-section, I illustrate our findings in the case of electron capture from rubidium 5s to sodium 3s at 2 kilo-electron-volt energy. In this first plot, I plot as a function of theta, the deflection angle, the weighted DCS. That is the DCS multiplied by the sine of theta, because it directly corresponds to the number of counts in the experiment. And we see that the agreement between the theory and the experiment is quite good. Furthermore, some oscillations clearly appear in the DCS. And we can check within the MOCC calculation that the angular spacing between these oscillations is the one which is expected for diffraction. So it is good, but we can say, do this really correspond to diffraction? Because if I plot not the weighted DCS, but the DCS as a function of theta, I observe here that the relative height of the peaks is quite strange. We indeed expect from diffraction that the height of the peaks progressively decreases as the angle increases. And this is clearly not the case. So to understand what happens, we have to realize that the C wave that is written here is a complex number with a phase which depends on B for a given velocity V. So if I cancel within this expression the phase, I obtain a typical diffraction spectrum. So what happens, in fact, is that the C wave is not fully coherent as a function of B. In other words, as they reach the slit, the nuclear trajectories are not totally spatially coherent, and this blurs the diffraction pattern. In this respect, as V is increasing, we see that the phase will decrease because of the 1 over V term. And consequently, the C phase will be more coherent, and we will obtain more normal diffraction shape. But to conclude already with this part, I will say that owing to the Motrim setup available in Caen with its very good resolution, we do observe genuine diffraction patterns, but which are blurred because the C wave is not totally coherent. So, and I have to say too that we did not resolve the diffraction patterns for all the charge exchange channels. We had some difficulties with the charge exchange channel for which capture can occur until very large value of Bmax. And this leads to prohibitive small angular spacing between the fringes, and we cannot resolve it. So I pass now to the second part of my talk, which deals with coherence with oriented targets. So I will present how the Motrim setup has been modified in order to obtain oriented targets. First, an homogeneous magnetic field is provided by Helmholtz coils. This sets the magnetic field B, and this sets the quantification axis Z. Then one of the mode trapping laser, which is secularly polarized, is used to orient the target. And the orientation depends on the endedness of the laser, as schematized in these two graphs. And we can obtain either rubidium 5p plus 1 state or rubidium 5p minus 1 state. This scheme is very simple, but I have to say that its implementation within Motrim is quite complicated. In this respect, the setup available in Caen, which merges Motrims with orientation techniques, is the only one which exists at this time, to my knowledge. Then now I pass to the theoretical description. I mentioned in the introduction that the orientation inherent here in the electron cloud destroys the cylindrical symmetry of the DCS. And that's really what is observed. And to understand that, we have to realize that the initial and final state I quantize in the X, Y, Z orientated frame, which coincide with the laboratory frame. But as soon as the projectile arrives, the subsequent collisional dynamics are described in the collisional frame with the z-axis in this direction, so that the laboratory and collisional frame do not coincide. So for a given E to F, I to F transition with I and F quantized in the laboratory frame, then the transition involves multiple collisional pathways because each of these states is a linear combination of scattering states defined in the collisional frame. I illustrate this here in the case of P plus 1 or minus 1 state. And we see that these oriented states are linear combination of PZ and PX collisional scattering states. The same linear combination affects the coefficient of the expansion of the total wave function as well as the scattering amplitude. As a result, the differential cross-section, which is illustrated here from P plus 1 to 4S collision, is formed by two parts. The first one, which I name incoherent part, in terms of non-interacting pathway, PZ and PX to 4S. And a second part, which involves products of T amplitude. So this is an interferential part. And we can see that within this interferential part, we have a cosine of phi term, and this term which ensures the asymmetry in the transit direction of the DCS. So now let's turn, excuse me. So now let's see how to measure the coherence because this is the aim of our study. So here the analogy with usual optics is very useful. We know that with a Young setup, we can measure the coherence of the two slits by measuring the visibility or contrast of the fringes. So here we do the same. As the DCS is formed by the incoherent part and coherent part, multiplied by the cosine of phi term, we can define, as in usual optics, the maximal and minimum intensity as a function of phi for a fixed theta, and then introduce the asymmetry parameter, which is the visibility, and which consists, as in the Young setup, of the ratio of coherent over incoherent part. And this is directly related to the coherence of the charge exchange dynamics. So the results. And first, for the main charge exchange channel from 5p plus 1 to 3p collisions. So in the first column of this graph, I represent the DCS in terms of its four main contributions, the left, right, down, and up contribution. And as expected, we see that whatever the collisional energy, the up and down contribution are symmetric. It's normal. While this is not the case for the left and right part. And this is typically very clear here at the smaller impact energy of 1 keV. I have plotted here the DCS as a function of E theta because according to the classical picture, this is directly proportional to 1 over B, where B is the impact parameter where the transition occurs. So we see that by varying the impact energy, the peaks are more or less at the same position. This indicates that the underlying mechanism is more or less the same. And we see that here at the lowest energy, some contribution appears at large E theta value, that is a small impact parameter. And this is due to the fact that at small impact velocity, the collisional system can enter into, evolves more adiabatically and enters the region of small internuclear distances. In the right column, I have plotted the asymmetry parameter, or the coherence parameter. And we see that there is strong oscillation as a function of theta. And it is worth noting that with previous orientation setup, which are able to access the coherence of the process, but which did not use neither rims nor mode, the resolution, the angular resolution, was of the order of 1 milliradian. So the observation of such an asymmetry feature would have been impossible. And we see that there is a strong oscillation. And this oscillation, the number of oscillation, increases as V decreases. And this is due to the fact that the phase is inversely proportional to the impact velocity V. Then we can see that even though the initial state of the collision process is totally coherent, we see that the dynamics can introduce some significant decoherence. But R can be as big as 0.6. So this is quite a coherent picture. Then I illustrate now the secondary electron capture channel that is the transfer from 5p21 to sodium 4s. And here I compare the experimental raw data with the MOCC calculation. And the agreement looks very satisfactory. But to have a more quantitative comparison, I compare here, as before, the DCS in terms of the left, right, up, and down contribution. And here, excuse me, the things are changing a lot because we see that all the distributions are formed by two peaks, which correspond to the two rings observed in the 2D plots. But while motrins provide a maximal autopeak, we see that this is the opposite in the MOCC calculation. So this means that usual MOCC fails. That is, we underestimate the transition at large E theta value, or in other words, as small import parameters. And this discrepancy is noticeable here in the asymmetry parameter for large theta values. So we have corrected this. And the improvement consists in accounting for the mutual polarization of the ionic core beyond the usual Coulomb repulsion. That is, to the VCC term, we add the ion dipole and dipole-dipole interaction term, which describes the polarization of the cores. And we see that this improvement makes the agreement of the calculation and experiment better. We indeed obtain now within the improved MOCC calculation that the outer peak is greater than the inner one. But some discrepancy remain, for example, about the location here of the outer peak, and we trace back the root of this later discrepancy to the use of the single active electron approximation. And we think that the molecularization of the ionic core should be accounted for. So I conclude very rapidly, Chairman. So our improved motrin setup has allowed to picture diffraction and incoherence pattern in sodium plus rubidium collision with unprecedented resolution, owing to the motrin setup of Kahn. And that the single active electron approximation is globally satisfactory, but its limitations have been revealed in the case of oriented targets. Very briefly, the motrin setup could be used for nuclear physics. This is the case at Argonne National Laboratory in the United States. And it could be used to characterize very exotic molecular states, such as this one. Such states are called trilobite systems, trilobite states. And thanks to you for listening. Sorry for the delay. And thanks to Arnaud Léred and Xavier Fléchard for LPC at Caen, Amine Kassimi and Dominique Encar, and Hervé Join from Bordeaux. OK, thank you.